Question 1 says, a biologist is studying the population growth of a species of birds on an island. The bird population P of t satisfies the differential equation dp dt is equal to 0.4p minus 0.001p squared. P of 0 is equal to 50, and t is measured in years. Part A says, what is the carrying capacity of the bird population? So we have our differential equation, and something that we should recall is that the logistic differential equation is of the form dp dt is equal to k times p times 1 minus p over capital M, where in this equation, capital M is our carrying capacity. So what we want to do is we want to get our differential equation in this form, and we're going to do that by factoring out 0.4p. And if we do that, that's going to leave us with 1 minus 0.001p over 0.4. And we want our coefficient for p in the numerator of this fraction to be 1. So I'm going to go ahead and simplify this fraction. If I move this decimal place over 3 places, that's going to give us 1. And then if I move this over 3 places, that's going to give me 400. So let's go ahead and rewrite this fraction. All right, so now that we've rewritten it, we can see that in the denominator, we have 400. So this is going to tell us that our carrying capacity in this case is 400, and then we are measuring a bird population, so it's going to be 400 birds. Part B says, when will the bird population reach 50% of the carrying capacity? So we're going to need to solve this differential equation and solve for P of t. Now, if you're taking my class, we have derived the formula for the solution to a logistic differential equation. But if you have not, you can always solve this using separable differential equations. So I've gone ahead and I've written the formula for the solution to a logistic differential equation, and we have P of t is equal to capital M over 1 plus capital A times e to the negative kt power, where capital A is equal to capital M minus P naught over P naught. And in this formula, capital M is our carrying capacity, and P naught is our initial population. So as we can see here, P of 0 is equal to 50. That is the same thing as P naught. So let's go ahead and calculate capital A. We have our carrying capacity from earlier was 400 minus 50 over 50. And this is going to end up equaling 7. Now, earlier we rewrote our differential equation. I'm just going to copy that down again really quickly. We found that dp dt was 0.4p times 1 minus p over 400. So that was our differential equation when we rewrote it. And from this, we can see that our k value is 0.4. So I'm going to go ahead and take all of that information to go ahead and plug into our population function. So capital M is 400, and capital A we just solved for, that was 7. And then I can replace k with 0.4, and here is our population function. So once again, here's our population function, and we want to know when the bird population will reach 50% of its carrying capacity. So what I'm going to do is I'm going to replace P of t with 50% of the carrying capacity, which is half of 400, and so that's going to be 200. And in this question now, what we'd like to do is we'd like to solve for t. Now, in this equation, if I divided both sides by 400, I would get 1 over 1 plus 7 times e to the negative 0.4t is equal to 200 divided by 400 is 1/2. At this stage, I can whatever technique you want to use. You can take the reciprocal of both sides of the equation, or you can cross multiply if that's what you'd like to do. That'll all give you the same answer. So I'm just going to take the reciprocal of both sides of my equation. I'm going to now subtract both sides by 1. Now I can divide both sides by 7. At this stage, we can take the natural log of both sides, and so on the left-hand side of the equation, that will give us negative 0.4t is equal to the natural log of 1/7. Then I can divide both sides by negative 0.4. Now, if you're taking my class, you cannot use a calculator on the final exam, and so you would leave your answer like this as an exact answer and not a decimal approximation, since you do not have a calculator. But in case you are curious, this ends up simplifying to be about 4.86. And we are solving for t, which is time measured in years. So this is just a way to say that the bird population will reach 50% of its carrying capacity in about 4.86 years. All right, so that's it for question 1. Question 2 says, evaluate the following integrals. In part A, we have the integral of the numerator is x minus 1, and the denominator is x times the quantity x squared plus 1, and then on the outside we have dx. So what I want us to do to start off this question is I want to split this up into 2 integrals. So my numerator, I have a binomial. So I'm going to split that up, and then I have minus 1 over x times x squared plus 1 dx. In my first integral, what's going to happen is these x's will divide out, and then I'm just going to have 1 over x squared plus 1, and the integral of that is going to be arctangent of x. In my second integral, I'm going to want to use partial fraction decomposition, so I'm going to come on do that off to the side here. Now, be careful in your second fraction. The denominator is going to be x squared plus 1. X squared plus 1 is an irreducible quadratic, meaning that the numerator needs to be something that's 1 degree less, which 1 degree less than a quadratic is a linear. So we want to write this as bx plus c. So now what I'm going to do is I'm going to use the method of clearing fractions and multiply every fraction by the least common multiple of all the denominators, which in this case is x times x squared plus 1. If we do that, we get 1 is equal to a times x squared plus 1 plus bx plus c times x. I'm going to go ahead and say let x equal 0. That will eliminate one of the capital letters that we are solving for. So the left-hand side is going to be 1. The right-hand side will be a times 0 squared plus 1. And then here, if we replace x with 0, that's going to make that whole term disappear. So this is going to simplify to 1, and so we get a is equal to 1. So let's replace those. Now I'm going to rely on the method of comparing coefficients. So I'm going to drop the 1 here, because if I distribute that in, it'll just stay the same. And then I can go ahead and distribute this x in. So my new equation will become 1 equals x squared plus 1 plus bx squared plus c times x. From here, if I subtract 1 on both sides, I'm going to end up getting 0 is equal to, let's see, I'm going to factor out x squared from the two quadratic terms, and that's going to leave me with 1 plus b x squared, and then plus cx. So what we can gain from there is we can see that c is equal to 0, because here we have our linear term. Here you can think about this as 0x, so then this implies that c is equal to 0. And then we also, if we compare the quadratic term on the right side with the quadratic term on the left side, we get that 1 plus b has to equal 0, which means that b is going to equal -1. So let's go ahead and replace those in back up here. So c was equal to 0, so we just are going to have -x there. Okay, so let's come down here and break up this integral. So we're going to bring down the minus sign, we're going to have minus, and then we'll end up having the integral of 1 over x dx. And now what I'm going to do is I'm going to distribute this minus sign in, because I'm really breaking up my integral into two integrals, so I need to distribute that negative sign. And if I distribute that negative sign, then we're going to get plus the integral of x over x squared plus 1 dx here. Now on this integral, I'm going to use u substitution, and I'm going to let u equal x squared plus 1, and then du is going to equal 2x times dx, and then if I divide both sides by 2, I get 1/2 du is equal to dx. So then I can rewrite this as 1/2 times the integral of du over u, or 1 over u times du, and that is going to end up equaling 1/2 times the natural log of the absolute value of u, which we define to be x squared plus 1, and then we would have our constant of integration. This thing is going to be the natural log of the absolute value of x. So let's go ahead and put everything together for a completed final answer. So our final answer is going to end up being arctangent of x minus the natural log of the absolute value of x plus 1/2 times the natural log of the absolute value of x squared plus 1 plus our constant of integration. So there is our answer for part A. All right, so for part B, we have the integral of, our numerator is x squared, our denominator is the square root of 4 minus x squared, and we are integrating with respect to x. This requires trigonometric substitution, and we are going to let x equal 2 sine of theta. And then dx is going to equal 2 cosine of theta d theta. So let's go ahead and rewrite our integral now with those substitutions. We'll have 2 times sine of theta quantity squared over the square root of 4 minus 2 sine theta quantity squared, and then we're replacing dx with 2 cosine of theta d theta. And then we can go ahead and do some simplification. If I square this term, that is going to give me 4 sine squared theta. And then here, same thing, underneath the square root, that would be 4 sine squared theta. And also underneath the square root, we can factor out a 4 from both terms. And 1 minus sine squared theta, using the Pythagorean identity, we can rewrite as cosine squared theta. Now, if I take the square root of that, that is going to give me 2 cosine theta. And oh, look at that. We have one in the numerator and we have one in the denominator, so that makes our life easier. So those will cancel out, and then this is going to turn into 4 times the integral of sine squared theta d theta. Now I recommend using the power lowering identity for sine squared, and so this will equal 4 times 1/2 the integral of 1 minus cosine of 2 theta d theta. So 4 multiplied with 1/2 is going to give us 2. And then from here, it might be helpful to split this up into two different integrals. So we'll have 2 times the integral of 1 d theta minus the integral of cosine of 2 theta d theta. And if we integrate, we'll have 2 times theta minus 1/2 sine of 2 theta plus our constant of integration. And sine of 2 theta, if we use the double angle identity, I know that sine of 2 theta is equal to 2 times sine of theta times cosine of theta. And so this 2 and this 1/2 will cancel out. So let's go ahead and clean that up. From here, I am going to distribute the 2 in. And although some of my students are inclined to stop here, our answer right now is in terms of theta, and our original integral, we were integrating with respect to x, so we need to get our final answer back in terms of x. The way that I'm going to go about doing that is I'm going to draw a right triangle and fill in some information there. So here is theta, and originally we know that we let x equal 2 times sine of theta, which if we solved this for sine of theta, we would get sine of theta is equal to x over 2. And so I know that my opposite side length to theta would be x, and the hypotenuse length would be 2. And then that would make the remaining side length, the adjacent side length, be the square root of 4 minus x squared. So now that we have this right triangle, it'll make it easier for us to fill in these values. So we have 2 times, and from this equation here, we can apply arcsine to both sides of the equation and get that theta is equal to arcsine of x over 2. And then we have minus 2 times sine of theta, we already know is equal to x over 2. And then looking at our picture here of our right triangle, we can see that cosine of theta is equal to the square root of 4 minus x squared all over 2 plus our constant of integration. And if you notice, there's a 2 in the numerator here and the 2 in the denominator. So if we clean that up, we can just put x there. And here is our final answer for part B. All right, let's move on to part C. So we have the integral of cosine of x times cotangent of sine of x dx. And here what we're going to do is we're going to use u substitution. And I'm going to go ahead and let u equal sine of x. And if I do that, then du will equal cosine of x dx. And I can go ahead and rewrite my integral as cotangent of u du. And from here, I'm going to go ahead and rewrite this as cosine of u over sine of u du using one of our trigonometric identities. And then I'm going to use a substitution again, and I'm going to let w equal sine of u. And then dw is going to equal cosine of u du. This will turn into 1 over w dw. And if we take the antiderivative of that, we'll get the natural log of the absolute value of w plus our constant of integration. And then we can sub w for sine of u. And then from earlier, we know that u is equal to sine of x. So finally, we'll get the natural log of the absolute value of sine of sine of x plus our constant of integration. And there's our answer for part C. In part D, we have the indefinite integral of x times the quantity e to the x plus e to the negative x dx. Now looking at this, I have the product of two functions, and so it might be worth trying tabular method, and I'm going to use our x value to go in the derivative column, and if I take the derivative, that's going to be 1, and then the next derivative will be 0. And the function that I'm going to integrate will be e to the x plus e to the negative x. If I take the antiderivative of that, I would get e to the x minus e to the negative x. And then if I took the antiderivative again, we would get e to the x plus e to the negative x. And I'm just going to draw my diagonal lines. The first one is positive and the next one is negative. So for part D, I have that the integral of x times e to the x plus e to the negative x dx is equal to, I have x times e to the x minus e to the negative x, and then we have minus the quantity e to the x plus e to the negative x plus our constant of integration. And here's our answer for part D. Question 3 says, apply the definition of the definite integral to evaluate the definite integral from 0 to 3 of x squared minus 5x dx. Now here, we specifically cannot use the fundamental theorem of calculus, and we have to use the definition of the definite integral. So we're going to start off by calculating delta x, which is equal to b minus a over n, and in this case, b is 3, a is 0, and then we have n. So our delta x value is 3 over n. So from here, now what I want to do is I want to calculate a formula for x sub I. And the general formula is a plus I times delta x. Here our a value is 0 plus I times 3 over n. And then if I simplify that, I'll get 3i over n. Now, we have that our definite integral is equal to the limit as n approaches infinity of the summation from I equals 0 to n of f of x sub I times delta x. So let's go ahead and fill those things in. So now I have the limit as n approaches infinity of my summation from I equals 0 to n of anywhere I see an x, I'm going to replace it with x sub I in my function, which is this thing here. So we're going to have 3i over n quantity squared minus 5 times 3i over n. And then we're going to multiply by delta x. Okay, now 3 over n in the i's of the summation is a constant, so we can factor that out. I'm going to have the limit as n approaches infinity of 3 over n times the summation from I equals 0 to n of, if I square 3i over n, that's going to give me 9i squared over n squared. And I'm going to distribute this 5 in, so we have minus 15i over n, like that. And now what I'm going to do is I'm going to factor out any constants outside of my summations, and also split this up into two different summations. So I'm going to take a moment to do that. All right, so I've gone ahead and I've split this up into two different summations and factored out anything that was a constant with respect to the summation. Now I'm going to go ahead and replace those sigmas with the formulas that we've learned earlier on. All right, so from here we can do a bit of cancellation. So this n and this n will cancel out. I can cancel out an n here and then one of the n's here. And let's go ahead and continue writing. So I have the limit as n approaches infinity of, I'm also going to take this step to distribute in my 3 over n. So we have the limit as n approaches infinity of 27 times n plus 1 times 2n plus 1 over 6n squared minus, let's see, 3 times 15 is 45. Then we'll have n plus 1 over 2n. Now, you'll notice that in both of these terms, the numerator and the denominator have the same degree, and so the limit as the input approaches infinity is just going to be the ratio of the leading coefficients. Now, just keep in mind, somewhere students will often make an error is there is a 2 right here, and so really the coefficient, the leading coefficient of the numerator should be 27 times 2. So please don't make that error and make sure you are aware of that. So the limit as n approaches infinity of, why don't we take out that 2? So we'll have 27 times 2 is 54 times n plus 1, and then if I factored out a 2, that's going to leave me with n plus 1/2 over 6n squared minus 45 times n plus 1 over 2n. And now let's just take the ratio of the leading coefficients. So let's see, 54 over 6 is 9 minus 45 over 2. And if you find a common denominator, this would be negative 27 over 2 or negative 13.5. Either of these are fine as a final answer. I just wanted to really quickly show that if I did end up using the fundamental theorem of calculus as a check, we do end up getting the same answer using the shortcut versus the longer way using the definition of the definite integral. But either way, both give us the same answer, so this tells us that we did this correctly. Question 4 says, consider a cylindrical tank with radius 3 feet and height 10 feet. If it is filled with a fluid that weighs 94 pounds per cubic foot, set up but do not solve an integral to find the work required to pump the fluid out of the top of the tank. Now, if you're in my class, something that I typically recommend for these types of problems is to draw a picture and to also make it so that the bottom of the tank aligns with or lines up with the x-axis. Now, there is an exception to that, and that's usually if you have a spherical tank, but in this case, we're not dealing with a sphere. So I'm going to have it line up with the x-axis, and then here is my y-axis. And what I'm going to do is I'm going to draw a cross-section of the fluid that is in this tank. So there is that. This is delta y, the thickness of this. And we know that the radius of the tank is 3 feet. So the distance from here to here is 3 feet. And we also know that the height of the tank is 10 feet. So we know that density is equal to mass divided by volume, and so if I solve that equation for mass, we get that mass is equal to density times volume. Now here we're actually not given the density of the fluid. We're given the information that the fluid weighs 94 pounds per cubic foot. And because we're in the US system and not the metric system, this dimension or this measurement that we're given is the weight density. And so what the weight density tells us is the force if we multiply it by the volume. And one way that you can think about that is I like to think about it with the units, because the units on this thing are 94 pounds per cubic foot. And so if I multiplied this by something that had cubic feet, what would happen is these would cancel out and it would leave me with a measurement of pounds, which is a measurement of force. And so what I want is I want to find the force, which is equal to the weight density and I want to multiply it with the volume. So if I'm looking at a slice of this fluid, it has the shape of a circular disc. And so the volume of this shape is the height, which we're calling delta y, and the radius, which is 3 feet. And because it's a circular disc, we have the volume of this disc, maybe I'll write disc down here, or slice, is equal to pi times the radius squared times the height. So this is equal to 9 pi times delta y. And so there is our force if we multiply those two quantities together. All right, so we found the force was 94 times 9 pi delta y. Now we want to find the work that it would take to pump this slice of fluid out of the top of the tank. And so that we know from earlier is equal to force times distance. So I'm just going to replace the force with 94 times 9 pi delta y. And then the distance that this slice of water is going to travel is, I know that, again, my total height of my tank is 10 feet. And I know that this is y feet high. And so the distance that it would need to travel is going to be 10 minus y feet. So here I will put 10 minus y. And the total work is we're going to need a definite integral. So my limits of integration are going to be, where does my bottommost slice of water, or not water, fluid start? In this case, it would be 0. And my last slice of fluid will end at y equals 10. And then we have 94 times 9 pi times 10 minus y, and then we have dy because we are integrating with respect to y. And if I wanted to factor out the constant, this is going to equal 846 pi times the integral from 0 to 10 of 10 minus y dy. And here is our answer. Question 5 says, evaluate the following improper integral or show that it is divergent. I'm going to use u substitution, and I'm going to let u equal 4 plus the natural log of x. That's going to mean that du is equal to 1 over x dx. And so my improper integral can be rewritten as the limit as b approaches infinity of the integral from 2 to b of 1 over, it might be helpful to think about it like this, 1 over x times 1 over 4 plus the natural log of x squared dx. And what's happening is 1 over x times dx will get replaced with du. So I'm going to rewrite this as the limit as b approaches infinity. We're rewriting our integral in terms of u, so I'm going to call my limits of integration u1 and u2, and then we're going to have 1 over u squared du. And it might be helpful to instead write this as u to the negative 2 power so that we can take the antiderivative using the power rule. So we have the limit as b approaches infinity of negative 1 over u. I increase the power by 1 and divide it by that new power. And we're evaluating this between u1 and u2. Now I can go ahead and put this back in terms of x. All right, so I went ahead and plugged in my limits of integration, and what's going to happen as b goes off to infinity, the denominator of this first fraction is going to get infinitely large, and this entire thing will go off to 0. So this is going to end up equaling 1 over 4 plus the natural log of 2, which ultimately means that our original improper integral is convergent. All right, question 6 says, consider the regions R1, R2, and R3 that are defined with the curves f of x equals 2/9 x squared and g of x equals 1/3 x plus 1. So we have these three regions that are defined by a parabola and a linear function. Part A wants us to find the ordered pair in quadrant 1 where the two curves f of x and g of x intersect. And then part B wants us to find the area of R2, which is colored in green in the image above. So let's go ahead and solve part A and B, and then we can go and solve the remaining parts of this question. So the two curves that we had were 2/9 x squared. And since they are both equal to y, or the output value, I'm just going to set them equal to each other. And I'm going to use the method of clearing fractions because I don't like fractions, so I'm going to multiply this entire equation, or every term of this equation, by 9, and that would leave us with 2x squared is equal to 3x plus 9, and I'm going to move everything over to one side. So we are left with this quadratic equation, and we can either factor or use the quadratic formula. I'm going to factor, and so I'm looking for two numbers that add to -3 and multiply to -18. And the way that I got these numbers is this is the b value, this is a times c, and the two numbers that accomplish this are -6 and +3. So now I'm going to rewrite this as 2x squared minus 6x plus 3x minus 9. So I had -6 and 3 now represent the coefficients of x, and essentially what we did was we broke up this term. Notice that if we combine like terms, it would return us to 2x squared minus 3x minus 9. And so now what we want to do is we want to factor by grouping. And if you've never factored by grouping, typically it's something you do when you have 4 terms. So I'm going to group these terms together and these terms together. And in the first grouping, I can factor out 2x, and that's going to leave me with x minus 3. And in the second grouping, I can factor out a 3, and that would leave me with x minus 3. And you know that you're doing factoring by grouping correctly if you have the leftovers being the same and matching up. So now I can factor out an x minus 3, and we have the 2x plus 3 still there. And now if I use the zero product principle and set both of these things equal to 0, I will get x equals 3, and I don't even really care about the second factor because it's going to give me a negative x value, and the question originally just asked us to find the ordered pair that's in quadrant 1. Now x equals 3 is not an ordered pair. An ordered pair looks like something like a comma b, and right now I just have the numerical x value. So how do I find an ordered pair? Well, now I can take x equals 3 and plug it into one of the two original curves. I'm going to plug it into g of x, which was 1/3 x plus 1. So if I evaluate g of 3, that's going to be 1/3 times 3 plus 1, which ends up simplifying to 2. So the final answer of where these two curves intersect in quadrant 1 is going to be the ordered pair 3, 2. The 2 is coming from there, and the 3 is coming from there. Let's go ahead and move on to part B. All right, part B wanted us to find the area of R2, and I just quickly drew a sketch to remind us, and we also found that the ordered pair where our linear or our line and our parabola intersected in quadrant 1 at 3, 2, so I documented that on my graph. And we want to find the area of the green shaded region, R2, and so I'm going to say that the area is equal to the definite integral from 0 to 3, because we're starting here at 0, 0, and we're integrating with respect to x. And if you remember from the area, or excuse me, the section on area between curves, it's the upper curve minus the lower curve. So in this case, the upper curve is the linear one, which was 1/3 x plus 1, and then minus the lower curve, which is 2/9 x squared. And now we want to go ahead and integrate. So I've gone ahead and taken the antiderivative, simplified, and then plugged in our limits of integration. Luckily, our lower limit is 0, so a lot of it will be 0. And then finally, if I go ahead and simplify this, it's going to give me 5/2 or 2.5 as the area of R2. Let's go ahead and fill in the information that we found in parts A and B. In part A, we found that our two curves f of x and g of x intersect at the ordered pair 3, 2. And in part B, we found that the area of R2 was 5/2 or 2.5. So I'm going to go ahead and cross those out just to illustrate that we have finished those. Now it says, for the remaining parts of this question, set up but do not solve the integral that would find the following things. In part C, we want to find the volume of the solid generated by rotating region R3 about the y-axis using the shell method. So R3 is the blue region, and I'm just going to go ahead and draw a quick sketch if we rotated about the y-axis. And it would look something like that. And if I drew a shell, it would look like this. And because our shell is going that way, that means that we are going to be integrating with respect to x because the thickness of our shell is delta x. And the other information we need to know is the radius, which is going to be the distance from here to here, and that is just going to be our x value, and then the height of our shell is the y value, but because we're integrating with respect to x, we want that to be in terms of x, so instead of y, it is going to be 2/9 x squared, because the height of our shell is touching the parabola, which was the f of x curve, again, which is 2/9 x squared. So let's go ahead and put all of that together for part C. We're going to have that the volume is equal to, we know when we use the shell method, we have 2 pi times the integral from, and then we are integrating from 0 to 3, because my first shell would start here at 0, and my last shell would end here at x equals 3. So those are our limits of integration. And then our radius is x, and our height is 2/9 x squared, and we are integrating with respect to x. Now, this is not necessary because you don't have a calculator, so I typically ask my students not to simplify numerically, but if I wanted to factor out the constant and multiply the x and the x squared together, that's going to give me 4 pi over 9 times the integral from 0 to 3 of x cubed dx. And again, it just asks us to set up but not solve these integrals, so maybe I'll just box this for part C. All right, part D says we want to set up the integral that would find the volume of the solid generated by rotating region R1 about the x-axis using the washer method. So I've gone here and just did a quick sketch of what we're doing, and we are rotating about the x-axis, and we want to use the washer method. So now I'm going to go ahead and draw a washer. So if I'm rotating about the x-axis, my washer is going to look something like that, and it's going to have a little bit of thickness to it. It looks like a little peach ring or a donut, whatever you want to call it. And the thickness of that is delta x or dx. And now we want to come up with our inner and outer radius. Now, if you move the cross sections along the x-axis, something that you will notice is that the outer radius does not change. That is to say, if you look at here from the x-axis, which is our axis of rotation, to the outer part of our washer, it's always this distance. I'm going to call it OR for outer radius, and that distance is always going to be 2, because we know that this ordered pair right here is 3, 2. Now, the inner radius is the distance from here to here. That's our inner radius. And notice that that's changing, and it's dependent on our linear function, which is 1/3 x plus 1. So let's go ahead and put all of that together. So for part D, we have volume equals, and then pi times the integral from 0 to 3. And then the formula goes the outer radius squared. So in this case, we said earlier our outer radius was 2. So it'd be 2 squared minus the inner radius squared, which is 1/3 x plus 1 quantity squared, and we are integrating with respect to x. So here is our answer for part D. Okay, so now we're on part E, which says we want to find the integral that would find the volume of the solid generated by rotating region R2 about the line x equals 5. So I've gone ahead and I've just done a quick sketch of the scenario that's happening here, and I want to go ahead and draw a shell. So we are dealing with region R2, and I'm just going to draw a quick shell here. So that's going to be dx or delta x, and then the radius of our shell is going to be the distance from our axis of rotation to that portion of the shell, and then we'll have our height of our shell. So let's start with the radius of the shell. I know that the distance from here to here is x, and then I know that the distance from my y-axis to the vertical line x equals 5 is 5, meaning that my radius is going to be 5 minus x. So with starting to write out our answer for part E, we have the volume is equal to 2 pi times the integral from 0 to 3 of my radius, which is 5 minus x. And then the height is going to be the linear curve minus the quadratic curve. So we have 1/3 x plus 1, and then we would subtract off the quadratic portion, and then we are integrating with respect to x. So there's our answer for part E. Now, if you read part E, it doesn't tell you that you need to use the shell method, and so there's actually a way that you could get the correct answer using the washer method as well. The thing about the washer method in this case, though, is that in order to get the correct answer using the washer method, you would need 2 separate integrals. And the reason for that is, if I were to draw a washer here, I can see my inner radius there, and then my outer radius is dependent on the vertical line that's here is the y-axis. And what happens is if I draw a cross-section higher up, the outer radius is now dependent on the curve g of x. So again, you could get the correct answer using the washer method. You would just need two different integrals. So I'll leave that up to you to think about what those integrals would be. Now we're on part F, which wants us to set up the integral that would help us find x bar, where x bar comma y bar is the centroid of R3. Now remember, the centroid is another name for the center of mass, which is, if you thought about R3 as a thin plate, where would I need to put like a pencil so that it would balance? And maybe it'd be like about right here, somewhere, maybe a little bit lower since it's bottom heavy, somewhere like right here. Maybe that's the center of mass, and right now we're trying to find the x coordinate of it. And if you need a refresher, x bar is equal to 1 over the area of the region that we're looking at times the integral from a to b of x times f of x minus g of x dx. Now, please be very careful. This f of x does not necessarily correspond to this f of x. In the formula, f of x just represents the thing that is the upper curve. So here, I'm just going to make a note. This is the upper curve. And this g of x is the lower curve. Okay, so let's go ahead and start to write our answer for part F. We have that x bar is equal to, now it tells us that we don't need to find the area of R3, and this is a final exam, so time is precious, and it just tells us to leave the area as capital A. So x bar is equal to 1 over a times the integral from, we're integrating from 0 to 3, and then we have x times. Now, f of x is going to be this thing here, which does happen to be the parabola, which is f of x here, but that might not necessarily be the case, so don't assume. It's just whatever's on top. And then the thing that's on the bottom is the x-axis here, which is the same thing as y equals 0. So really, in our formula, we just need 2/9 x squared, and then we have dx. And if you want, you can factor out the constant and multiply x times x squared. And if we do that, then we get 2 over 9 times capital A on the outside of our integral, and then our simplified integrand would be x cubed. So that's our answer for part F. Part G wants us to set up the integral that would find the arc length of f of x from the origin to the point that you found in part A. So let's go ahead and highlight that. F of x is the parabola, so we are setting up the integral that would find the arc length of this curve between x equals 0 and x equals 3. And if you need a refresher, the formula for arc length is equal to the integral from a to b of the square root of 1 plus dy dx quantity squared dx. This is one version of the arc length formula, and this is the one that we're going to use. And because we are dealing with the parabola, I can think of this as y equals 2/9 x squared. I'm going to use that formula to find dy dx. And if I use the power rule, we're going to get 4/9 times x. So for part G, our answer is the arc length is equal to the integral from 0 to 3 of the square root of 1 plus the derivative squared. The derivative we just found was 4/9 x. And we are integrating with respect to x. So here are all the answers for the various parts, the several various parts of question 6. Question 7 says, given that h of x is equal to the integral from 1 to 4x of t over 1 plus t squared dt, we would like to find h prime of x. So we definitely want to use the fundamental theorem of calculus part 1, But the fundamental theorem of calculus part 1 requires that the upper limit of integration be just a single variable by itself. Here's a statement of the fundamental theorem of calculus part 1, and because our upper limit of integration is not just a single variable by itself, we just have to do a slight alteration. Now, at the beginning of the quarter, I showed you how to do this, and the reason that this occurs is because of chain rule. I'm okay with you, if you're in my class, just kind of using the shortcut now. And so the shortcut is you take the integrand, so in this case we have this thing here, and our input variable is t because we're integrating with respect to t, but now what we're going to do is anywhere we see the input variable t, we're going to replace it with 4x because that is our upper limit of integration. And then the other thing we need to do is we need to multiply the entire thing by the derivative of the upper limit of integration, which the derivative of 4x is 4. And if we clean this up a little bit, 4 times 4 is 16. So I get 16x over 1 plus, and then I can square 4x if I'd like to. And we get that this is equal to h prime of x. So here is our answer for question 7. Question 8 asks us to solve for the explicit solution of the differential equation dp dt is equal to the square root of p times t, and we're also given the initial condition p of 0 is equal to 2. So first things first, I know that I can split up the square root because underneath the square root we have a product. So I'm going to rewrite this as the square root of p times the square root of t. And this is a separable differential equation. So I want to kind of move around the sides, and this is going to give me dp over the square root of p is equal to the square root of t times dt. And I'm going to rewrite this on both sides so that it's easier to integrate. And I can end up using the power rule. So I'm going to have p to the negative 1/2 power is equal to t, oops, I forgot dp, is equal to t to the 1/2 power dt. And from here, I can integrate both sides, and I would use the power rule. So on the left-hand side, I would increase the power by 1, which would now be 1/2. And then I want to divide by that new power, and dividing by 1/2 is the same thing as multiplying by 2. On the right-hand side, I'm going to increase the power by 1. That's going to give me a new power of 3/2, and I am going to divide by the new power, which is the same as multiplying by the reciprocal. And then I would like to include my constant of integration, which here I'm just going to call C1. Now we are solving for the explicit solution. That means that we are wanting to isolate P in this equation. So my next step is I'm going to divide both sides of this equation by 2. And if I do that, I get P to the 1/2 power is equal to, if I divide 2/3 by 2, that is going to give me 1/3 t to the 3/2 power plus C1 divided by 2. Now, C1 divided by 2 is just some constant, so I'm going to replace that and just call it a different constant with the label C sub 2. From here, I'm going to square both sides because I would like to isolate P, and by squaring both sides, that's going to help me out. So then I would get capital P is equal to 1/3 t to the 3/2 power plus C2 squared, and that is our general solution, but we are given P of 0 is equal to 2. Remember that this thing is called an initial condition, and the initial condition is going to help us find the particular solution. So P of 0 is equal to, anywhere I see AT, I'm going to replace it with 0. And we know that this quantity is equal to 2. So from here, I'm going to erase this part, and I'd like to take the square root of both sides. Also, 1/3 times 0 to the 3 halves. This whole thing is equivalent to 0. So I'm going to end up getting C2 quantity squared is equal to 2. If I take the square root of both sides, we get C2 equals plus or minus the square root of 2. And now I can go ahead and plug that information back into my general solution. And that's going to give us P of t, or just P, is equal to 1/3 t to the 3 halves plus or minus the square root of 2 quantity squared. And there's our answer for question 8. Question 9 says the graph of a function f of x is shown to the right. Use the graph to estimate the definite integral from 0 to 8 of f of x dx using the trapezoidal rule and 4 subintervals. In other words, we'd like to find t sub 4. Your final answer needs to be a simplified number. So let's go ahead and find delta x. So I know that delta x in general is equal to b minus a over n. Our b value is 8, our a value is 0, and our n value is 4. So we have 8 divided by 4, which is equal to 2. So the width of each of our subintervals is 2, and since we're dealing with integers mostly, this shouldn't be too bad. We're starting at 0, and then our next subinterval will be starting at 2, our next one will start at 4, our next one will start at 6, and then our last one will start at 8. And let's kind of write out the formula for t sub 4. We have t sub 4 is equal to delta x over 2 times f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6, and then plus f of 8. So remember, in the formula for trapezoidal rule, all of the terms except the first one and the last one are being multiplied by 2. So now all we need to do is fill in the values. We found delta x to be 2, so 2 divided by 2 is 1. Now f of 0, we are just reading these values off of the graph. F of 0 is -1, and then we have 2 times f of 2 is 1, 2, 3. So that's going to be 3. And then we have 2 times, if you look at f of 4, that is 0 off of the graph. Then plus 2 times f of 6 is +1. And then lastly, f of 8 is equal to 2. So my first term is -1 plus 6 plus 0 plus 2 plus 2. And if we simplify that, that is going to be equal to 9. And there is our final answer for question 9. That concludes this video where we went over a Calculus 2 final exam. Thanks for watching, and we'll see you next time.